This lecture is going to cover a confidence interval for a proportion. We're going to try to estimate a population proportion using what we call a confidence interval. And how we're going to think about a confidence interval is by taking this example. Here we're going to try to estimate the proportion of collegiate students in a relationship. So using data from previous quarter's students, 47 out of 125 students identified as being in a relationship. If we were to find the proportion, we would take the successes, quote 47, out of the total number of observations, 125. And we would end up with a proportion of about 0.376. The question that we need to think about, should we say 37.6% or a proportion of 0.376 of all college students are in a relationship? Should we use that exact value to estimate our population proportion? Think about this for a second and pause the video if need be. Hopefully we've come to the conclusion that no, we should not be using this exact value to estimate the proportion of students in a relationship in college for all students. There's variability from sample to sample, right? If we took another sample of 125 students, we would probably end up with a different result, a different number of successes. There is variability to sampling. So just because you get a result in one sample doesn't mean that's going to happen for the next one. On top of that, if we think about proportions, how likely is it that exactly 0.376 is the proportion of all college students in a relationship? How likely is it exactly that number? If we think about proportions, right, proportions range from 0 to 1. Now, while there's a finite population size, it's a very large population size of all college students. So if we want to think about this, essentially there's an infinite amount of decimals between 0 and 1. And the fact that we're guessing exactly one outcome out of an infinite amount of possibilities, this quantity would equal 0. So essentially, there's going to be a 0% chance that we're right. Now, technically, since there is a finite number of observations, it would be 1 over a very large amount of observations, which is about 0%. So using one specific value is not a good method in order to estimate a population parameter. What we're going to do instead is this. We're going to construct what we call a confidence interval. A confidence interval creates a range of values using our sample statistics that will estimate our parameter to be within a certain level of certainty. Instead of guessing one value and being essentially 0% confident, let's guess a range of values, and in doing so, we'll be a lot more confident than 0% that we're estimating the parameter that we're interested in. Let's see a little visualization of what I mean by this. We're going to look at a simulation to represent this concept. Now, something that we don't know is pi. Pi stands for our population proportion. And we're trying to estimate the proportion of collegiate students in a relationship. So suppose, for argument's sake, this is something we would not or do not know, but suppose in reality the proportion of all college students in a relationship is 0.34982 and so on and so forth. What we're doing is we're trying to take a sample of 125 observations to estimate this proportion. So watch what happens. We're going to take a sample, simulate a sample, and it's going to spit out a certain number of successes and a certain number of failures. Down here, it's plotting our sample proportion, which in this case was found to be 0.384. This visualization over here is representing our sample proportion and our population proportion. This black line, this theoretical black line, while it's rounding it, it's representing our population proportion of 0.34982 and so on and so forth. This little black dot represents our sample proportion. I'm going to simulate another sample. So another sample of 125 observations. This time we got 0.432. And notice the little black dot, again, it does not fall on this vertical black line. Our goal is to estimate this vertical black line. We actually don't know what this is. In this example we do because we're pretending we know what the population proportion is, but this is our mystery. This vertical black line, this population proportion is a mystery to us. And so I'm just going to keep hitting new sample. Each time we get a different sample proportion, sometimes that black dot is really close to the population proportion, that vertical black line, but it's not exactly on it. 0.360 is not exactly 0.34982. And I can click this until I have gray hair, but that little black dot, while it will get close, will never fall exactly on that population proportion. I clicked this 60 times, and all 60 of those sample proportions did not fall on that black line. I can make this and do 100 samples at the same time. We're making 100 different sample proportions. And notice I simulated this concept over 1,000 times, and none of those sample proportions fell exactly on that black line. This is why we can't use just one value to estimate a population proportion. We need to use a range of values. So here's what we're going to do. We're going to take a sample of 125 observations, but now we're going to want to be more confident. Let's try to be more confident than 0% that we're going to capture our parameter. So I'm going to increase our confidence level to some arbitrary number, which we'll see why I choose this shortly, but 95%. And let's calculate a sample. So we'll notice in this example, we got a sample proportion of 0.304. That little black dot represents 0.304, which does not fall exactly on our vertical black line, our population proportion. However, the interval that we created using that sample proportion does capture that black line. We are estimating our population proportion using an interval as opposed to a single value. We can select another sample and notice again that black dot does not fall exactly on our line. That black dot is 0.384, yet our confidence interval is capturing it. I'm going to simulate this 100 times. So every time I hit sample, you'll notice the red intervals do not capture the black line and the green ones do. So I'll hit another sample of these, another sample of these, another sample of these. We ran 402 confidence intervals and 376 captured our population proportion, that vertical black line. Notice we've been making 95% confidence intervals, yet only 93.5% of our confidence intervals had captured our black line. Why is that? If we were making 95% confidence intervals, shouldn't 95% of those intervals capture our black line, our population proportion? Well, here's the thing. Let's think about flipping a coin. Right? If you flip a coin 100 times, half the time you're going to get heads, half the time you're going to get tails. But are you guaranteed 50 heads and 50 tails if you flip a coin 100 times? No, you're not. There's variability. There's randomness. The only way we can guarantee that this percentage would be 95% is if I just clicked sample an infinite amount of times. If I just kept hitting sample and sample and sample and we did more and more confidence intervals. That's the only way we can get this to be close or exactly to that 95%. What we can learn from this is if we created an infinite amount of confidence intervals, 95% of them will capture that black line. But we're obviously not going to create an infinite amount of confidence intervals. So another way we can think about this is we're 95% confident that the interval we create would capture our population proportion. Let's go back to some notes. The reason I chose 95% as our arbitrary confidence level is because it's one of the values of our empirical rules. Right? Our empirical rule says if we go a certain number of standard deviations each way on a normal distribution, we'll capture a certain percentage. 68, we had to go 1 standard deviation each way. 95, we had to go 2 standard deviations each way. And 99.7, we had to go 3 standard deviations each way. So by creating a 95% confidence interval, we were going 2 standard deviations away from our sample statistic. Now let's see how we would calculate those confidence intervals that we were looking at.